Greetings, students, and welcome to today's exploration of a fascinating problem in the realm of algorithms and data structures. We will delve into LeetCode problem 33, which presents us with the intriguing challenge of searching for a target number within a rotated sorted array. Imagine, if you will, an array of integers that has been meticulously sorted only to be rotated around a certain pivot point. Our objective is to locate the index of a specified target integer within this altered array. Should the target be absent, we are to return -1, signaling its non-existence. To illustrate, consider the input array, 4, 5, 6, 7, 1, 2, with a target of 0. Here, the number 0 resides at index 4, thus our output would be 4. This problem not only tests our searching prowess, but also invites us to think critically about optimizing our approach given the array's unique structure. Let us embark on this intellectual journey together. The binary search technique is a powerful algorithm designed to find a target value within a sorted array. Imagine a book where you know the page numbers are in order. Instead of flipping through each page one by one, you can open it to the middle, check if the target page is higher or lower, and then decide which half to search next. This is the essence of binary search. It systematically eliminates half of the potential candidates with each comparison. To implement binary search, you start with 2 pointers, one at the beginning and one at the end of the array. You calculate the middle index and compare the middle element to your target value. If they match, you're done. If the target is smaller, you continue searching in the left half. If it's larger, you move to the right half. This halving process continues until you either find the target or exhaust the search space. Binary search operates with a time complexity of O log n, making it incredibly efficient, especially for large data sets. Understanding this technique is essential in computer science, as it highlights the importance of data organization and efficiency in algorithms. Let's dive into the binary search technique using the example of searching in a rotated sorted array. First, we define the function binary search, which takes in a sorted array R and a target value we want to find. We start by establishing 2 pointers, left at the beginning of the array and right at the end. This sets our search boundaries. Next, we enter a while loop that continues as long as left is less than or equal to right. Inside this loop, we calculate the midpoint index, mid, which helps us narrow down our search. We then check if the midpoint value is the target. If it is, we return the index. If the target is greater than the midpoint value, we adjust the left pointer to focus on the right half of the array. Conversely, if the target is smaller, we move the right pointer to focus on the left half. If we exit the loop without finding the target, we return -1, indicating that the target is not present in the array. This efficient method allows us to quickly locate values, even in a rotated sorted array. Left-right pointer manipulation is a fundamental technique in computer science, particularly useful for working with arrays. Imagine you have an array lined up in front of you. The left pointer starts at the beginning, while the right pointer begins at the end. As you navigate through the array, these pointers move toward each other based on specific conditions determined by the task at hand. This approach is efficient because it minimizes the need for additional space and complicated loops. For example, if you're trying to find 2 numbers that add up to a certain value, you can simply adjust the pointers depending on whether the current sum is too high or too low. By moving the left pointer to the right or the right pointer to the left, you effectively narrow down your search. This technique not only speeds up the process, turning what could be a slow, quadratic search into a much quicker linear one, but also keeps your code clean and easier to debug. By leveraging the relative positions of the pointers, you can efficiently explore the array and achieve your goals. In this slide, we see a function called reverse array, which takes an array as input and reverses its elements. Let's break it down step by step. First, we initialize 2 pointers, left and right. The left pointer starts at the beginning of the array, while the right pointer is positioned at the end. This setup is crucial because it allows us to compare and swap elements from both ends of the array. Next, we enter a loop that continues until the left pointer meets the right pointer. Inside the loop, we swap the elements at these 2 pointers. Imagine this as a game of passing items across a table, We're exchanging the items at both ends. After the swap, we move the left pointer one step to the right and the right pointer one step to the left. This brings us closer to the center of the array with each iteration. Finally, when the loop completes, we return the reversed array. This method effectively flips the order of elements using a straightforward and efficient approach, making it a great example of pointer manipulation in action. Optimized time complexity analysis evaluates how efficient algorithms are by examining the time they take to run as the input size increases. We use big O notation to express this, which represents the upper limit of an algorithm's runtime. For example, if an algorithm runs in O(n) time, it means that as the input grows, the execution time grows linearly. Understanding this concept is critical in computer science because it guides developers in selecting or designing algorithms suited for specific tasks. It helps identify potential bottlenecks in code, ensuring applications run smoothly, especially in performance-sensitive environments like large-scale systems or real-time applications. Analyzing time complexity involves examining an algorithm's structure, including loops